temperature, circulation decreases, so keep moving, wiggle your toes.
All right, so let's take a look at 11.5, solutions to uranium fuel limitation. Okay, so one thing is making use of all secondary sources like we talked about, the nuclear fuels, reprocessing plutonium in the form of a mixed oxide fuel, an existing reactor, so just a little bit of recycling. Taking the spent fuel from the PWRs and putting them into the CANDUs, which require less high concentration. Breeding more plutonium. And I might have mentioned last time, but when I was at Drexel University, one of my colleagues had visited the Chernobyl site, sort of told that war story a little bit, and, said something a little bit puzzling to me. He goes, well, nuclear reactions are the one rare exception to reactions where you get more out than you put in. And I think what he's talking about there is plutonium. So if plutonium's coming out, it still has a very high energy content. It's more volatile, more explosive, less stable, but I think that's more or less what he meant by that. Longer term, be made more fuel efficient, high operating temperatures. What's going on there with higher operating temperatures? What do they mean? What's the big deal about higher operating temperatures and efficiency?
It creates more steam, right?
Yeah, so fundamentally, all these nuclear reactors are, in fact, heat engines. They're heat engines, right back to Chapter 4 and Chapter 6. And so the efficiency is just this. It's the high temperature minus the low temperature over the high temperature. If you ever have trouble remembering this equation, because this will come into any energy technology efficiency equation. Well, not any, but if you get into wind, it doesn't apply to wind. But any heat engine operates by this Carnot equation. If you have trouble remembering it, here's how you do it. There's really only two numbers on the right-hand side. And you know that the high number is bigger than the low one. So you subtract the low one from the high one. So you got a minus sign in the middle, and you got the big one on the left and the small on the right. What goes in the denominator, should it be the high temperature or the low temperature? Well, if you remember your third law of thermodynamics, you know that the lowest temperature you can get to is about 0 Kelvin. You don't want a 0 down here. So it's got to be the high temperature. It's going to be the bigger one. And so, for example, and this is super simple, but if you say my high temperature is 600 Kelvin minus 300 Kelvin. Oh, and by the way, to do this equation properly, it has to be done in Kelvin. Divided by 600 Kelvin, you end up with 1/2. So there's there's your thermal efficiency. Well, how do you make this better? Well, you jack up that temperature, right? So if you've got if you go to 900 minus 300 over 900 equals 6 9 equals 2/3. Even better, right? So just keep getting hot. At some point, you don't have the metallurgical technology to build turbine blades that can withstand this type of temperatures. There are limits to everything, but that's what they mean by. Funny, my little bar went away up top there. Okay, so higher temperatures, closed fuel, reprocessed plutonium, fast breeder reactor. So a fast breeder reactor is going to use uranium-238 instead of 235. We talked about 235 last time being the fuel of choice because it's less stable than 238. And we already mentioned this technology could be taken further to breed uranium from thorium. So you could take all of what the thorium laying around and turn it into uranium. And then finally, if we get there, fusion power could become the energy of the future. All right, so secondary is just tailstocks from enrichment, weapons grade, or repurposing from existing. So there it is. I do know on the exam that MOX is going to be there, so just remember MOX. Uranium is a metal, and there's a lot of oxygen around, and in general, just think of MOX as rusty uranium. You know, it's just uranium combined with oxygen, or rusty plutonium.
Leave it in the backyard, don't rain too much.
Yeah, don't leave it out back. It says as of 2009, approximately 6% of the world's reactors were licensed to use MOX. Okay, here we go. This is the number I was looking for. So here's plutonium. It says in 2000, the U.S. and Russia agreed to dispose of 34 tons each of weapons-grade plutonium. I do not know what the disposal means. If that just means that it goes into back in the ground somewhere, if it goes, I shouldn't even say back in the ground, because almost all the plutonium on planet Earth has been made by humans. It doesn't, you don't dig it, you don't mine it. 34 tons each. In 2007, the UK had 100 tons sitting around that could be used for MOX fuel. Now, the CANDU, as I mentioned, can run on a very low 0.7%, 235. So you could take fuel that's got most of its 235 spent and put it in the CANDU. Thus reducing the uranium requirements by 30%, so not too bad. Now, it says nuclear power stations under pressure to maximize the energy output, of course, from a given amount of fuel, of course. Minimize operational downtime, so just keep the thing running. I think that's part of what led to Chernobyl's disaster. And minimize the volume of waste. So these three objectives can be achieved to some degree by what they're calling a burn-up, a measure of the total heat produced by a ton of uranium. Okay. So here we go. Early reactor designs says the Magnox using unenriched fuel with 235 of 0.7 have a burn-up of around 5 gigawatt days per ton. Now, that does not mean that much matter is being turned into energy. We did the E equals MC squared earlier. I mean, that many tons is not being turned into energy. Like, that many tons is enough to run the planet forever. So it's just how much is being converted or unenriched. Oh, I like this one too. So, study by MIT in 2003 said that a future improvement going from 50 gigawatt days. So, we've heard megawatt hours. This is gigawatt days per ton to heading up to, so doubling that, getting 100 gigawatt days per ton would half the spent fuel production. Sorry, I'm just going to pause it for one quick second. Hey, sweetie, are you okay?